So if we have a look at this circuit, we've got a resistor in series with a capacitor in series with an inductor. And we've got an AC supply power in that circuit. So we need to be able to work things out with circuits like this. So we need to be able to work out how much current this circuit is going to draw, amongst other things. So if we have a look at this circuit, we can see that it's a series circuit. So the current is going to flow in one big block through all the components and back to the source. So if we put the current in, the current is going to be going through the resistor, it's going to go through the capacitor, and it's going to go through the inductor. And those three currents are the same current, so they're going to be in phase. Now the resistor has resistance, and we know that in a resistor, current and voltage are in phase. So we can put the voltage in there as in phase. The capacitor has capacitive reactance, and we know that in a capacitor, current leads voltage by 90 degrees. So we can put the voltage in there. And in an inductor has inductive reactance, and we know that in an inductor, voltage leads current by 90 degrees. So if we put the voltage in there, we can see that we can't just add these values up because they're not in phase. They're all over the place. So we need to have a way of adding these values up. So if we look at, we've got resistance, we've got capacitive reactance, we've got inductive reactance, and the total opposition to the current in this circuit will be what we call impedance. Impedance is the total opposition to current of a circuit, and it takes into account the resistance and the reactance, both capacitive and inductive. So we're going to look at ways that we can work the impedance out of a circuit. Okay, so we're given the components in this circuit values, and we're going to attempt to work out the impedance of this circuit. So we're given the resistance, a resistance of 2.5 ohms. We've given the capacitive reactance of 2.5 ohms, and we've given an inductive reactance of 5 ohms. So we're going to try and work out what the impedance is going to be. So the first thing I'm going to do is I'm going to draw phasors in on the circuit diagram, and I'm going to scale the phasors to the length of the reactance or the resistance, and I'm going to give them a direction following the direction of the voltage across that component. So the first value we're going to put in is the resistor, so I'm going to scale that at 2.5 because it's 2.5 ohms, and that's the voltage across the resistor is in phase with the current, so we'll keep that in phase with the current, so we'll make that horizontal. And then we'll go to the capacitor, so that's got a reactance of 2.5 ohms, so I'm going to scale the arrow 2.5 ohms long, and the current is leading the voltage in a capacitor. So the voltage is pointing down if the current is horizontal. So we'll put the phasor pointing down. And then we'll get to the inductance. So the inductance has a reactance of 5 ohms, and the voltage is leading the current in an inductor. So we'll point that reactance or that reactive phasor pointing upwards. Okay, so we'll take the circuit diagram off, and we'll plot these phasors onto a phasor diagram. So we'll plot the resistance on the x-axis, we'll plot the reactance of the capacitor and the inductor on the y-axis. So the first thing to notice is that the capacitor has a negative value. So we're going from the origin and we're pointing down, so it's got a negative value. Now a capacitance or a capacitive reactance always has a negative value. So I can add two phasors together by moving one phasor to the end of the other phasor, and the resultant addition of those two phasors will be from the tip of the second arrow down to the origin of the first arrow. So we're going to add the capacitance to the reactance of the inductor. So I'll move the phasor for the capacitive reactance up. So the base of that is on the tip of the inductive reactance, and the resultant of those two vector additions is this vector here, or this phasor here. Okay, so I'm going to move that resultant value to the end of the resistance. So we're going to add that to the resistance, and the resultant value of that is the impedance of this circuit. So we've got what we call an impedance triangle, or we've ended up with an impedance triangle, where the impedance is the hypotenuse, the opposite side is always the reactance, and the adjacent side is always the resistance. We call that the impedance triangle. So this is the impedance triangle from the last slide. We've got Z on the hypotenuse, we've got a right angle triangle, we've got resistance across the bottom, and we've got reactance up the side. And we know what the resistances and the reactances are, so we can use Pythagoras to work out what the impedance is. So Z is the square root of R squared plus XL plus XC squared. Now we know that XC is negative, so that is impedance equals the square root of 2.5 squared, that's the R, plus 5 plus minus 2.5 squared. So Z equals the square root of 2.5 squared plus 2.5 squared, so Z equals 3.54 ohms. Now, the impedance lines up with the voltage. The resistance lines up with the current. So the angle between R and Z is the phase difference between voltage and current. And we can work that out because we now know Z, so we can use cosine. So the inverse cosine of resistance divided by impedance, which equals 2.5 divided by 3.54, which equals 45 degrees. So in this circuit, overall, the current is lagging the supply voltage by 45 degrees. We've got the impedance of the circuit now, so now we can work out the supply current, or the current being drawn by this circuit. And to do that, we can use Ohm's law. So V divided by Z. So IS, supply current, equals V divided by Z, which equals 10 divided by 3.4, which equals 2.82 amps. So the circuit's drawing 2.82 amps. And we know from the previous slide that the current is lagging the voltage by 45 degrees. So now we've got IS, we can work out the volt drop across each of the components in the circuit. So we can work out VR by using Ohm's law. So VR equals I times the resistance. So VR equals 2.82 times 2.5 ohms. And that gives us a volt drop across the resistor of 7.05 volts. And we can work out the volt drop across the capacitor by using Ohm's law. So VC equals IS times XC, the capacitive reactance, which is 2.82 amps times 2.5 ohms, which gives us 7.05 volts. And we can do the same for the inductor. So VL equals IS times XL. So VL equals 2.82 times 5 ohms. And that gives us a volt drop of 14.1 volts. So looking at those volt drops across those components, they seem a bit wrong. We've only got a 10 volt supply voltage, and yet we've got 14.1 volts across the inductor. And we've got 7.05 volts across each of the other components. They don't look right, but they are right, because those voltages are all pointing in different directions, and the phasor sum of all those voltages will equal 10 volts. So let's take a moment to look at what we've learned in the last few slides. So we've learned that impedance is the total opposition to current in the circuit, and impedance is given the symbol Z. So that's the combination of all the resistors and reactances in the circuit. We can work out the impedance by using Pythagoras. So Z is the square root of R squared plus XL plus XC squared. But we've got to remember that XC is always negative. It's measured in ohms, so Ohm's law applies. And the phase difference between voltage and current is given by the inverse cosine of R divided by Z.